So today we're going to be looking at lesson 9.6, and we're going to be creating equations given complex roots. So creating equations of polynomials. So before we get to doing that, let's think about roots and their factors. So when we think about our factors are when we write them in parentheses. So our root or our zero that we were doing in last chapter was, say, x equals 2. Well, we always say, okay, well, it's the opposite. So we would have x minus 2 as our factor, and then x equals 2 is the 0. Well, when we're solving for our 0, we would have x minus 2 equals 0, and we add over 2, and that's where we get x is 2. Well, we can also go the reverse. If we have x equals 2, in order to get this side with the 2 equal to 0, I can move my 2. So that's where my factor comes from, x minus 2. And then that's equal to 0, which is what our equation's equal to. So my factor here would be x minus 2. X equals 0, well, if I subtract over 0, it's just x. So my factor is x. Or x, same thing as x plus 0, but there's nothing there. So if I have x equals negative 4/3, well, I can't just say x plus 4/3. I have to go a little bit further with that. So off to the side here in blue, if I have x equals negative 4/3, well, I want to get my side with negative 4/3 equal to 0. So I have to move everything over to the side with x. Well, if I'm dividing by 3, to move that 3, I have to multiply by 3. So I have 3x equals negative 4, and then I would add over 4, giving me 3x plus 4 as my factor. And then I can always solve for my 0 to make sure that it is, in fact, the correct factor. So these are ones that we've done before. So x equals 2, it was the same thing if we had, say, x equals negative 1. Then we'd have x plus 1 as our factor. What if we have complex roots? So what if we have x equals plus or minus 2i? Well, remember our complex conjugate theorem. If we have positive 2i, we also have to have negative 2i. So here, positive and negative 2i. So we will always have both. So here, let's do this in purple. So I'm going to have the opposite. So I would have x plus 2i and x minus 2i. But we don't want i's in our factors because when we multiply it out to get our function, we don't have imaginary numbers in there. So in order to get the factor, we then just have to go ahead and multiply this out. So we have x plus 2i, x minus 2i. If we go ahead and multiply here, so I have x times x gives me x squared. X times negative 2i is going to be negative 2ix. And then 2i times x is going to be positive 2ix. And then 2i times negative 2i is going to give me a negative 4i squared. Now this is always going to happen because of our complex conjugates or opposites. Those middle terms are always going to cancel out. So here, the ix's are always going to cancel. So I'm just left with x squared minus 4i squared, but we know that I squared is negative 1. So we have x squared minus 4 times negative 1, which gives us x squared plus 4. So that would be my factor of my positive and negative 2i. So I would have x squared plus 4. And if I were to go ahead and solve that, subtract over 4 and take the square root, I would see that positive and negative 2i are in fact my zeros, my roots there. So this here is my answer. This would be my corresponding factor to positive and negative 2i, x squared plus 4. So now let's go ahead and look at our last one here. So we have x equals 7i. Oops. So if I have x equals 7i, I cannot possibly just have 7i. So it's not just x minus 7i is my factor. If I have x minus 7i, I also have to have x plus 7i. It will always be true that I have both. So x minus 7i and x plus 7i will always come together. They always come in pairs. And this is why they always come in pairs, because when we multiply them out, then we get our factor there. So if I go ahead and multiply this through, I'm going to get x squared plus 7ix minus 7ix minus 49i squared. So these two middle terms are going to cancel, and I'm going to be left with x squared minus 49, and I squared becomes -1, so x squared plus 49. So this would be my factor for 7i, because I know it has to be positive and negative 7i, even if I'm only given 1. All right, so this says find the equation of the function with factors of x plus 3i and positive and negative 3i. So I'm going to go ahead and break this down into two different functions. I'm going to start by finding factored form, and then we're going to go ahead and multiply it out to find standard form. So factored form is with our factors. So here we're given x plus 3 already, so I know that's one of my factors. And then I have to find the other one from my complex root here. So if I have 3i, positive and negative, I know that I have x plus 3i and x minus 3i. So this would then, I can go ahead and multiply these out to find the factor with my integral coefficients. So they don't have complex numbers. So if I go ahead and multiply this out, I have x squared, and I'm going to have my middle terms that are going to cancel. And then my final term of -9i squared. So my middle terms cancel, and I'm left with x squared minus 9 times -1. So my factor is x squared plus 9. So I have x plus 3 times x squared plus 9. So this would be my function in factored form. Now we're also going to ask you to go ahead and then put that in standard form. So this would be factored form with my factors. So then standard form would be going ahead and multiplying that out. So standard form then, I would take x plus 3 and x squared plus 9 and multiply those out in order to get those polynomials that we're used to seeing. So I would take x times x squared, which is going to give me x cubed, x times 9, which is going to give me 9x, 3 times x squared, 3x squared, and then 3 times 9, which is going to give me 27. Now, this is multiplied out, but when I write it in standard form, I want to make sure that I go in order from highest degree to lowest. So I want my largest exponent all the way down to my constant. So in standard form, my function would be x cubed plus 3x squared plus 9x plus 27. So here is what an equation or a function looks like in standard form, multiplied out. This is what we tend to see. And then here is factored form, which is before I'm going to go ahead and multiply this out. It just gives me my factors, which I can find my zeros from. So factored form and standard form. So here's one last example. It says find the equation of the graph with zeros of x equals 3, x equals -1, and x equals 4i. So breaking it down again, we want to start by finding the equation in factored form. So in factored form, I'm going to take my zeros and rewrite them as factors. So the ones that are not complex, my real roots, are pretty straightforward. So I'm just going to move it over to the side with x. So if I have x equals 3, I'm going to subtract it over. So I'm going to get x minus 3. X equals -1 would add over to the other side, so it will become positive, x plus 1. And then I have x equals 4i. So looking at this, it's like, oh, this is a cubic because I have 3 zeros. But I have to remember my complex conjugate theorem, my complex root theorem, and know that my complex have to come in pairs. So if I have 4i, I also have -4i. They have to come together. So when I go ahead and write this, I have x plus 4i and x minus 4i. Then I have to go ahead and multiply out to find my factor. So when I do this, I get x squared and my middle terms, 4xi and negative, because those are going to cancel. And then I'm here have -16i squared. So x squared, my middle terms cancel, and I have -16 times -1, because remember I squared is -1. So my factor is going to end up being x squared plus 16 when I fully simplify that. So this would be my function in factored form here. And I have, if I look, I have 1, 2, 3, 4 x's. So this is a quartic, 2 complex, 2 real. If I then want to go ahead and find standard form, I'm going to have to go ahead and multiply this whole thing out. So what I would do is I'd take my first 2 binomials and I'd multiply them together and then go ahead and multiply it into the last one. So I'm going to start by multiplying x minus 3 and x plus 1 together. And then I'll multiply that into x squared plus 16. So I'm going to take this and multiply it out. So I get x squared plus 1x minus 3x minus 3. And I'm going to have to end up multiplying that by x squared plus 16. So this I can simplify down a little bit further to get x squared minus 2x minus 3. And I'm going to take that trinomial and multiply it into this binomial. So now instead of just taking the first 2 terms and distributing them in, I have to distribute all 3 terms in. So if I'm going to go ahead and do that, I'm going to take x squared and multiply it in. So x squared times x squared and x squared times 16. So bringing that up here, I'm going to get x to the 4th plus 16x squared. So that's multiplying my first term in. Now if I multiply -2x in, I have -2x times x squared, which is going to give me -2x cubed, and then -2x times 16, which is going to give me -32x. Then I'm going to multiply in my next term, and that is going to give me -3 times x squared and -3 times 16. So if I have, move this over, if I have -3 times x squared, I have -3x squared, And then if I have negative 3 times 16, that's going to give me negative 48. So a lot of multiplying out here, but now I can just combine my like terms to get my final function. So I only have 1x to the fourth, 1x to the third term. I'm going to combine my x squareds, so that's going to give me plus 13x squared. Then I have 1x term, so I have negative 32x minus 48. So this would be in standard form multiplied all the way out. And remember we said that we have 4 zeros, so it should be a quartic, which it is. It is of degree 4. So I at least know that I have that first term correct here. So I have x to the fourth minus 2x cubed plus 13x squared minus 32x minus 48 as my polynomial in standard form.